The moment it happens, there is no warning siren, no countdown, no visible shockwave rolling across the horizon. Lights simply die. Not flicker, die. Vehicles stall mid-motion, aircraft lose instrumentation, communication networks dissolve into silence, and across entire regions, the invisible backbone of modern civilization collapses in less than a second. An electromagnetic pulse, whether generated by a high-altitude detonation or a severe solar event, does not destroy buildings or ignite fires in the conventional sense. It targets something far more critical and far more fragile, the integrated electronic nervous system that modern life depends on. And what makes this threat uniquely dangerous is not just its speed, but the widespread misunderstanding of what actually fails, what survives, and what equipment truly matters in the aftermath. The common assumption is that an EMP is a kind of universal kill switch, frying everything electronic instantly and permanently. That assumption is only partially correct, and that partial understanding is where most preparation fails. The reality is layered. An EMP consists of multiple components, each interacting differently with electrical systems. The initial fast pulse, known as E1, can induce high voltages in microelectronics, overwhelming circuits that were never designed to handle such spikes. The slower E2 component behaves similarly to lightning, something many systems are already somewhat protected against. The final E3 is slower still but far more insidious, inducing currents in long conductors like power lines and pipelines, effectively overloading transformers and grid infrastructure. It is not the flash of destruction that causes long-term collapse. It is the silent, cascading failure of interconnected systems that were never meant to operate independently. What most people misunderstand is the difference between device failure and system failure. Not every electronic device will be destroyed in an EMP event. Small, unconnected electronics may survive, especially if they are not plugged into long conductive lines that act as antennas for the pulse. However, the infrastructure that supports them, power generation, distribution networks, communication relays, can be severely compromised. This creates a paradox where individual devices may remain functional, but the systems that give them purpose no longer exist. A radio that works without a network, a vehicle that starts without fuel distribution, a medical device without supply chains. These become isolated fragments of capability in a landscape of systemic failure. The hidden science behind EMP vulnerability lies in electromagnetic coupling. Conductors of sufficient length can capture and channel energy from the pulse, concentrating it into connected systems. Power lines, telephone wires, and even long stretches of metal infrastructure act as unintended receivers. This is why grid transformers are particularly vulnerable. They are connected to vast networks of conductive pathways that amplify induced currents. Once damaged, these transformers are not easily replaced. They are large, custom-built components with long manufacturing lead times, often measured in months or years. The destruction of a relatively small number of these critical nodes can disable power across entire regions for extended periods. Evidence for this vulnerability is not theoretical. Historical data from solar storms, such as the Carrington event of 1859, demonstrated the capacity for geomagnetic disturbances to disrupt telegraph systems across continents. More recent events, like the Quebec blackout in 1989, showed how even less intense geomagnetic activity can collapse modern power grids. Controlled testing by defense agencies has repeatedly confirmed that certain classes of electronics are highly susceptible to high-frequency electromagnetic impulses, particularly when connected to external wiring. These findings are not speculative. They are grounded in decades of research in electromagnetic compatibility and infrastructure resilience. The implications of this are not centered on dramatic destruction, but on prolonged deprivation. Water systems fail when pumps lose power. Food distribution halts when refrigeration and transportation networks collapse. Medical facilities become overwhelmed when backup systems are exhausted. The timeline of impact is measured not in seconds but in days and weeks. The initial event is merely the trigger. The real crisis unfolds as dependencies unravel. And this is where the concept of a gear list becomes critically misunderstood. Most preparedness lists focus on obvious items: food, water, flashlights, and batteries. These are necessary, but they do not address the deeper issue of functional continuity. The question is not simply what you have, but what continues to work when systems fail. This distinction reveals a category of equipment that is often overlooked, not because it is hidden, but because it operates outside the assumptions of normal life. Devices that are not connected, systems that are manually operable, tools that do not rely on complex supply chains, these become disproportionately valuable in an environment where automation and connectivity have collapsed. One of the most critical yet underestimated principles is electrical isolation. Equipment that is physically disconnected from conductive pathways at the moment of an EMP event has a significantly higher chance of survival. This is the basis for protective measures like Faraday enclosures, which block electromagnetic fields from reaching sensitive electronics. However, the effectiveness of such protection depends on proper construction, grounding, and sealing. Improvised solutions often fail because they overlook the importance of continuous conductive shielding and the elimination of gaps that allow energy to penetrate. Another overlooked factor is the distinction between solid-state electronics and electromechanical systems. Older technologies, such as analog radios or vehicles with minimal electronic control units, are inherently more resilient. They may not offer the efficiency or convenience of modern devices, but they operate on principles that are less susceptible to high-frequency electromagnetic interference. This does not mean they are immune, but their failure modes are different and often less catastrophic. Understanding this difference is not about nostalgia, it is about recognizing the engineering trade-offs that define resilience. The evidence supporting these distinctions comes from both laboratory testing and real-world observations. Military standards for electromagnetic hardening require systems to withstand specific levels of induced voltage and current, and equipment designed to these standards consistently demonstrates higher survivability. Civilian devices, by contrast, are rarely built with such conditions in mind. Cost, size, and efficiency take precedence over resilience to rare but high-impact events. This creates a gap between what is commonly available and what is truly reliable under extreme conditions. The implications extend beyond individual devices to entire strategies of preparedness. A collection of advanced tools is of limited value if they all fail simultaneously. Conversely, a smaller set of robust, independent tools can provide sustained capability. This shifts the focus from quantity to quality, from accumulation to functionality, and it introduces a critical concept: redundancy across different technological levels. Having multiple ways to achieve the same outcome, communication, navigation, water purification, using different underlying principles increases the likelihood that at least one method remains viable. As the escalation escalates, the interplay between surviving equipment and failing systems becomes more pronounced. Communication, for example, is not just about having a working radio. It depends on the presence of others with compatible equipment, operating on agreed frequencies within range. Navigation is not just about having a GPS device. It requires satellites, ground stations, and timing signals that may no longer be reliable. Even basic tasks like cooking or heating become complex when fuel distribution networks are disrupted. Every layer of dependency reveals another point of vulnerability. This leads to a critical transition in understanding. The question is no longer what should you have, but what will still function when everything else stops. The answer lies not in mainstream lists, but in the intersection of physics, engineering, and practical survival logic. It involves identifying systems that can operate independently, tools that can be maintained without specialized infrastructure, and methods that do not rely on fragile networks. It requires a shift from convenience to resilience, from optimization to durability. And as the analysis deepens, it becomes clear that the most important gear is not necessarily the most advanced or the most expensive. It is the gear that aligns with the realities of electromagnetic vulnerability and systemic collapse. It is the gear that acknowledges the difference between surviving an event and sustaining life in its aftermath, because the true danger of an EMP is not the moment it strikes, but the silence that follows, and what you're left with when that silence becomes the new normal.
The silence that follows is not empty. It is filled with the consequences of systems that have stopped communicating with each other. In the first hours, there is a deceptive calm as people attempt to restart devices, reset breakers, or wait for services to return. This period is defined by uncertainty, and uncertainty drives behavior that often worsens the situation. The danger is not immediate violence or chaos, but delayed recognition. Most individuals are conditioned to expect restoration, to assume that outages are temporary. This assumption creates a critical delay in transitioning from dependence to self-sufficiency, and it is within this delay that the first layer of failure expands. The analysis begins with a simple but often ignored reality. Modern infrastructure is not designed for rapid, manual fallback. Water systems rely on electrically powered pumps to maintain pressure and distribution. Without power, gravity-fed reserves begin to deplete and pressure drops across the network. What remains in pipes becomes vulnerable to contamination as backflow and leaks introduce external elements. The misunderstanding here is that stored water exists in large quantities and will continue to be accessible. In reality, the accessible portion is limited, and the mechanisms that deliver it are electrically dependent. Once pressure is lost, even intact supplies become difficult to retrieve. The hidden science behind this lies in fluid dynamics and system design. Municipal water systems operate under carefully regulated pressures to prevent contamination and ensure consistent flow. These pressures are maintained by pumps that respond dynamically to demand. When power is removed, the system does not simply stop, it destabilizes. Pressure gradients shift, valves behave unpredictably, and the integrity of the distribution network begins to degrade. Evidence from past infrastructure failures shows that water systems can become unsafe within hours of power loss, even if the source remains uncontaminated. The survival implication is clear. Access to water is not just about quantity, but about the ability to extract, transport, and purify it under degraded conditions. This leads directly into one of the most overlooked categories of equipment: non-electric water acquisition and purification tools. The common approach focuses on stored water and powered filtration systems, but these are finite and often dependent on replaceable components. Gravity-fed filters, manual pumps, and chemical purification methods operate on principles that do not require external power. Their effectiveness is rooted in basic chemistry and physics, adsorption, mechanical filtration, and microbial inactivation. However, their limitations are equally important. Flow rates are slower, maintenance is manual, and the burden of operation shifts entirely to the user. This is not a flaw, it is a trade-off that becomes acceptable when the alternative is no access at all. As the timeline extends, the failure of communication systems introduces a new layer of isolation. The danger here is not just the loss of information, but the fragmentation of situational awareness. Without reliable communication, individuals and groups operate based on incomplete or outdated data. This increases the likelihood of poor decision-making, resource misallocation, and unnecessary risk-taking. The misunderstanding is that communication is synonymous with digital connectivity. In reality, communication is a spectrum of technologies, each with different dependencies and vulnerabilities. The hidden science in communication resilience lies in frequency propagation and power requirements. High-frequency signals used by many modern systems rely on infrastructure that may no longer be functional. Lower-frequency signals, particularly those used in certain types of radio communication, can propagate over longer distances with less reliance on intermediate relays. This is why certain analog radio systems, especially those designed for emergency use, remain viable when more advanced networks fail. The evidence for this is well documented in disaster response scenarios, where amateur radio operators often provide the only reliable long-distance communication in the immediate aftermath of infrastructure collapse. The survival implication is not simply to possess a radio, but to understand how to use it effectively. This includes knowledge of frequencies, propagation conditions, and power management. A device without operational knowledge is functionally equivalent to no device at all. This principle extends across all categories of gear. Tools are only as effective as the user's ability to operate and maintain them under stress and without external support. As conditions deteriorate, the focus shifts to energy, not in the abstract sense, but in the practical ability to perform work. The danger here is the assumption that stored energy, such as batteries, will provide a long-term solution. Batteries degrade, deplete, and eventually fail. The analysis must consider not just storage, but generation and conversion. Solar panels are often cited as a solution, but their effectiveness depends on several factors: exposure, orientation, storage capacity, and the resilience of associated electronics. Without proper protection, charge controllers and inverters can be as vulnerable as any other electronic device. The misunderstanding is that renewable energy systems are inherently resilient. In reality, they are systems composed of multiple components, each with its own vulnerabilities. The hidden science involves the conversion of energy from one form to another and the inefficiencies and dependencies that arise in that process. Evidence from off-grid installations shows that while solar systems can provide sustained energy, they require careful design, maintenance, and protection from environmental and electromagnetic threats. The survival implication is that energy solutions must be layered, combining generation, storage, and direct use methods that minimize reliance on complex electronics. This brings into focus another category of overlooked gear: direct mechanical tools. Devices that convert human effort into useful work, hand pumps, manual grinders, mechanical tools, operate independently of electrical systems. Their efficiency is lower and their operation is labor-intensive, but they provide a baseline capability that does not degrade with the loss of infrastructure. The escalation here is not in complexity, but in effort. Survival becomes a function of energy expenditure, and the balance between input and output becomes critical. As the environment stabilizes into a new baseline, the interplay between available resources and operational capability defines the trajectory of survival. The transition from short-term response to long-term adaptation requires a re-evaluation of priorities. Equipment that was once considered secondary becomes primary, and convenience is replaced by necessity. The hidden gear list is not a collection of obscure items, but a framework of thinking that prioritizes independence, redundancy, and resilience. The next phase of analysis moves deeper into the vulnerabilities of transportation and mobility, systems that are often assumed to be reliable, but which depend on a complex network of electronic and logistical support. Because movement, whether for evacuation or resource acquisition, becomes one of the most critical and most misunderstood challenges in a post-EMP environment.